Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to just do an introduction into the electronics unit of our overall course. Now we saw in the electromagnetism unit that basically we can produce an AC current by the process of electromagnetic induction. Using Faraday's and Lenz's law, we were basically able to understand that by interacting two magnetic fields, we could generate a force on the electrons. Those electrons were then moved through a wire. This movement of charge through the wire was basically current. Now, in the Western world, basically we generate something called AC current or alternating current, and it produces a sine curve, as you can see in the diagram here. This is as a direct result of the poles keep continually changing. As the poles continually change, what we get is force is actually acted on the electrons in two different directions. So we get a positive and a negative. Now you'll notice that the peaks of the voltages or the EMF which is produced are the same distances apart. So there's the same maximum force as we move through the oscillation of our, or the rotation of our armature. Now, what we need to do is, that's fine when we're dealing with the production of current, but for electricity flowing through an appliance, to have the charge continually being switched, or the EMF continually being switched from positive to negative through zero, it's like flicking the light switch on and off and on and off and on and off and on and off and on and off. You get the idea. It's not good for the circuit. So what we want is a continuous flow of charge, or a continuous flow of current. This is where we come across DC current or direct current. This is where current basically is at a nominal amount, and it will also have a certain amount of energy. Your appliances basically are designed to work with a certain amount of energy, and as a result you don't want them to fluctuate. The only time that you will fluctuate your DC voltage is when you switch your appliance on and off, and there are components within the actual appliance which will allow a steady increase in voltage until it's at its nominal rate. Now, if you think about the old TVs used to take time to warm up, and it's a similar sort of process which is occurring here. So what we need to know is, how do we go from AC to DC? How does this happen? Well, basically it's down to two major components, and this is what we're going to look at in our electronics unit for the rest of this topic. Now, the two things, or the two components that we're going to be looking at, are capacitors. As you can see here, we've got a capacitor and a capacitor working in a circuit, and we've got diodes, and you can see the diodes here. The left-hand diagram is a diode, and you can see again how it's been incorporated into an electronic circuit. Okay, so during this this second unit, we're basically going to be looking at how do capacitors work and how do diodes work. But what I'd like to do is give you an overview as to how they work, so that you can see the big picture, and then we can go in and make it more detailed as to looking at those individual components. Well, basically what happens is we get an AC curve, which we can see generated here. You can see it's got voltage up the y-axis. We've got a positive and negative end to it. So positive obviously above the white line, negative below the white line. Now obviously this flicking between one and the other is not good. So what we actually want to do is to try and get it all above the line. So what we want to do at these 2 points here is to take those troughs and basically put them at the top. Now this is done using a diode. So the diodes have the effect of allowing to put the bottom half of the curve, or the negative part of the curve, above the line. So we get these two humps. Now even so, these four humps, sorry, even so this is not good, because we're going from 0 volts to a maximum, then down to 0 to a maximum, then down to a 0 to a maximum. Appliance still doesn't like that. So somehow we've got to, at these points here, we've got to try and smooth off the curve. We need to have a delivery system where the voltage is being applied to the appliance as the AC coming in from the mains is dipping down to zero. And this is done with a capacitor, where it delivers energy at these 2 points to smooth off the peaks. So while it's dropping down to zero, the capacitor has the effect of delivering energy until the AC curve begins to build up again. Now the result of that, as you can see down the bottom here, is what we get a fully rectified DC voltage. So you can see that we get these bumps. It's sometimes called the ripple effect, and it's due to the fact that we're trying to get that DC. So you can see that we've gone from the bumps of the AC, or the sine wave of the AC, to then little bumps, and then we've smoothed off those little bumps as best we can. The more capacitors we use, or by using filtering, we can smooth off that line until eventually we get a nice straight line. So, as I said, how do they do this? Well, this is what we're going to be looking at during this unit. We will look at capacitors in detail, and we'll look at diodes in detail. Okay, so we're aware now that I think that we need to know how to go from AC to DC. But there's another law that we've got to apply, and that's the law of conservation of energy. Remember, the AC will have a certain amount of energy, and that's got to be converted into DC. So what we want to do is to produce a curve which we can see in the diagram here, where we've got a circuit, we've got a CRO, which is a cathode ray oscilloscope, which I've shown earlier, and we want to produce that nice straight line from our curve line. Now, if you look at the graph and the second diagram, you can see that the peaks are coming out at a maximum level. We call it VP, or the voltage peak of the AC. Now, if you think about it, if I was to take that negative peak, which is trough down, and build it up so that I get those little humps again, each one of those the area covered is going to be energy. Now, there's going to be gaps in that energy, which means that if there's gaps in that energy, in order to get a nice flat line, that whole area that you can see in the left-hand diagram, everything below the horizontal line is going to be the energy, and that's got to come from the AC, which stands to reason that the maximum voltage that you get in AC cannot be the same voltage as the DC. So what's got to happen is we've got to have this law of energy of conservation. What we start with is what we finish with. So we are going to be expecting that the DC voltage will be lower if we've got an AC voltage which is peaking at certain positions. So let's try and explain that in a little bit more detail. Well, you can see here's the diagram that I showed you earlier. So remember, we've got to conserve all that energy. Now we know that the red dotted line is the AC voltage peak. That's the maximum alternating current or voltage that is produced by that alternating current. Now we can see that if we add a capacitor in there, we can smooth off some of the energy. But basically what we want to know is if we've got an AC voltage which is peaking at a specific level, what's the actual energy when we relate it to DC? Well, it's got to be lower than what we started with. So what we need to be able to do is have some form of method to determine how much energy is actually incorporated in our DC voltage. Remember, voltage is joules per coulomb, the amount of energy which is given to a coulomb of charge. Okay, so you can see there that that white dotted line is basically lower than the red dotted line, or the ACV peak, voltage peak. And what we're basically stating is that those top portions of the peaks basically will fill in the bottom portions, or the gap portions of our peaks as we go through. So basically we need an algorithm which is going to allow us to convert from one to the other. Well, there is one. We can calculate the DC Vmax, which is the same as what's known as the DC VRMS, or root mean square. Now basically how to work it out is very simple. We use the algorithm that you can see here. Now you don't need to understand the mathematics behind where the algorithm comes from, but basically all it's trying to do is to try and fill in those little triangles from the peaks of the AC, and saying how much do we cut off from the peaks to fill in those little gaps to get a nice rectangular curve on our graph, and that's our energy. So what we do is we use VRMS equals VP over root 2. where VP is going to be the peak voltage generated by the AC current. VRMS is going to be the DC voltage, which is basically being produced by that peak voltage from AC. And obviously root 2 is just a constant. So to reiterate this again, VC, to get the maximum DC current, it's going to be the root mean square of the maximum peak voltage of AC. So let's have a look at an example. So if I've got a peak AC of 240 volts, what I want to know is what's the DC equivalent. So to run through this, I know I'm trying to find VRMS, and I know that VP is going to be 240. So I use VRMS equals VP over root 2, which means I've got 240 volts divided by root 2. So my VRMS is 169 volts. So 240 AC will equate to 169 volts DC. Okay, well I hope that makes sense and has given you a sort of overview as to how or what we're going to be looking at with respect to our electronics package. Remember, we're going to go into real detail looking at capacitors and diodes. So I hope you found that useful, and thanks for watching, and I look forward to you joining me again.